Okay. Good morning, everyone. Um, so last class, we began talking about linear models and thinking about uh, how we estimate it, interpreting the betas, the coefficients, in other words, in our sort of univariate model, just the slope of the line, understanding about standard errors. And so today we're going to continue our discussion about thinking about what it means for a model to be good. So one of the first things that I wanted to do to both familiarize ourselves with the concept of understanding what the standard errors and the R squared. We concluded last time with that example of the Anscombe quartet where we're looking at 4 different models that had identical R squareds and standard errors, but were actually fitting on really sort of different sorts of data. And so I think today, what we want to do to start off is to actually look at calculating some of these metrics manually, and then thinking about how we're using them to judge the quality of the model. Okay, so let's go ahead and do a calculation of a couple models, both the standard error and the R squared, but we're actually going to do it by hand instead of using the built-in functionality so that we can customize some parts of it. Okay. So first off, I'm going to load up a couple libraries. So hopefully you guys are familiar with these by now. So data table and ggplot, which we've covered. And then actually, I'm also going to be using something called calplot so that I can show ggplots side by side. So this is going to be our common, a sort of common motif or common way I'm generating some of this data. This is exactly the same as last time, randomly drawing from a uniform distribution, 100 points between 0 and 50, and then we'll have a deviation. Again, this is same as last time. And so the deviation is going to be from a normal distribution of 100 points with a mean of 0, standard deviation of 5. And our true model is going to look like this. So one of the handy things about sort of doing this approach in generating data that I'm kind of using as an example to regress to is that we know the true form of the regression and the true form of the relationship between y and x, which oftentimes you don't. And this is going to let us do a couple neat things with the diagnostics. So I'm just going to make a table real quick of these data. And then we're going to run a regression model. Okay, so hopefully, especially if you've reviewed some of the notes from last time. This should be pretty familiar. Essentially, we've created an artificial data set of X's and Y's, and then we run a simple linear regression against it, and then the summary is going to give us essentially, hang on. The summary is going to tell us the estimated coefficients of the model and the standard errors. So this is our estimate, 0.52 with standard error 0.03785. Again, the true model relationship between X and Y we know to be 0.5 because that's how we've sort of defined our data initially. And we can modify a second example. And this is going to be the same thing, except that the deviation is going to be twice as large. Okay, and so I'm just going to quickly throw this together, and we'll take a look at what these models are describing in a hot second. So again, this is putting together an example regression, except that our error term essentially is twice as large. And let's take a look at what this looks like. So I'm actually just going to copy and paste this part. And this code is just plotting. Well, I'll show you what the plot looks like. But in terms of understanding what this ggplot is doing, I would say refer back to the previous lecture. And I'm generating two plots and then using the cal plot to put them side by side. Oop, didn't run model 2. So let's take a look here. So these are the two regression models that I've just produced in example 1 and example 2. They are exactly the same, except that each of these individual points are going to be essentially twice as far from the line, right? Because we've multiplied our deviation by 2. And so what we can see is that the spread is a lot wider of points compared to in example 2 compared to example 1. And what we're going to try and do now is to manually estimate our standard errors and our R squared. And in doing so, one of the things that's we can do is to actually calculate a different beta, for example, and look at what the standard error would be, so that we're not actually looking at the optimal sort of line from a linear regression. So let's see, we'll have a function called manual standard error. And again, this will be calculating it by hand. So as a quick refresher, let me pull up my notes to make sure I don't get this wrong. Okay, let me jump over to a whiteboard really quick. So from the last lecture, I had written this out. So just as a reminder, we're gonna essentially learn how to code this manually in a function in R. And so the standard error of a particular coefficient, say beta 1, is equal to the sum of yi minus yi hat squared. So this is simply the difference between your true value, your true y value, and your predicted y value. So in a plot, that would be something like this. If this was our regression, yi minus yi hat is the corresponding distance here. And so we take that, we square it, divide by n minus 2, and all of this over xi minus the mean of x squared. So this would be the average value of x and looking at the distance to that average value. Okay, so keep that in mind for the standard error, and then for our r squared, 1 minus the sum of yi minus, so same thing here. Yi minus yi mean squared. Okay, and so the r squared, as again, a quick refresher, is essentially a comparison of how my regression line that I fit through data like this would compare to a line that would just be the mean of my y values. That's essentially what the r squared is telling us. So let's go back to RStudio so that we can see how to code these manually. Okay, so let's see the inputs here. We need to know our y and then our beta and our x. So the reason why you didn't see this in the equation is that we calculate our y hats via our x's and our betas, right? And so that's what we're going to do here. So the numerator is the sum of y minus y hat, which we don't have. And so y hat is equal to x times our beta. And so it's this quantity squared over the length of y minus 2. Oh, I need to pull my chat back up. Okay. And then in our denominator, we have the sum of x minus the mean of x squared. And the value that we're concerned with, the output, is the square root of the numerator divided by the denominator. We're going to return our output. So this, sorry, force of habit. So this function essentially takes in a vector of x's and y's and a value of beta and gives us the standard error for that corresponding beta. And then we'll make an r squared function as well, and we need the same inputs. Okay, so then our numerator is y minus y hat, which is x times beta. We'll square that. Have a denominator, and this is the sum of y minus the mean of y squared. So that would be essentially the error between your points and a flat line of average value of your y's. And our final r squared is 1 minus the numerator divided by the denominator. Okay. Great. So now that we have this, let me run this. Oop, what's this? Not sure what this warning message is, but that's all right. We'll sort of move on. Okay, and so, okay, why am I doing this? Let's get to our sort of punchline. So I'm going to manually get at standard error of a wrong coefficient. Okay, and so we know that the best fit for this set of x and y's, we know that the true value is equal to 0.5. But here I'm actually going to put in a coefficient value of 0.45, and I'm going to do the same thing for my r squared, and we'll calculate that. So this is example 1 modified to imperfect beta. And here's my example 2 modified to correct beta. So we're going to do a standard error here, xy to 0.5, and manual to xy2 0.5. And let's take a look at what the values are generated here. Okay, so this, let's see, in model 1, or in example 1, we have a standard error of this with an r squared value of 0.64, whereas in example 2, we have this standard error with an r squared of 0.297. Okay, so now let's think about this sort of qualitatively. When we when we talk about standard error and we talk about R squared, um, this sort of harkens back to what I was talking about last time, where oftentimes people consider these two values to be the metric of success, okay, and how good the model is. But we can empirically demonstrate that even for a data set of essentially the same sample data, that interpretation of your standard errors and how significant they are in interpretation of the R squared, if you were to take those sort of at face value, then you may sort of say that this first example is a superior model to example 2. And to a degree, you would be right in the sense that you're getting sort of closer, predictions. But one of the interesting things is that we know the true value of our coefficient, right? Because it's coming from an artificial model that we ourselves created, and yet you can see that when we have correctly identified the right slope, the right coefficient in example 2, in other words, we are replicating the correct model to the empirical form of the model. You end up having a less significant standard error, and you have a smaller R squared than in the model where you have the actual incorrect coefficient. And so all of this is sort of trying to demonstrate this point that that relying on just these metrics as sort of the sole goalposts for the quality of your regression model can lead you to sort of misinterpret the strengths and weaknesses of the actual model that you've done. And so hopefully this example helps to demonstrate that, right? We can see that you are technically getting, quote unquote, a better model that we know to be wrong than a model that we know to be right. Okay. So that is sort of the last bit of stuff that I'll say regarding our discussion of standard error and R squareds. So if anyone has any questions, you can feel free to chime in now. Hang on, I saw a message pop up. Yes, okay. So just to reiterate, to reiterate what I've done, we've manually calculated standard error and R squared for an incorrect model that and that's estimating the slope at 0.45, which is why I created the manual function. And the whole point is to demonstrate that when I compare this set of data versus another set of data where I'm correctly representing the coefficient value, you actually get a better model with the wrong slope, just because of the way that the data is ranged. And so if we were to rely on standard error and R squared to say that it's a better model, you would actually be just saying that the incorrect model is better than the correct model. Okay. So let's move on to talking about residuals. Okay, so residuals are the deviation between your observed value and estimated value. So this is the proper term for this thing that I've been referring to about your errors. So this would be your y minus y hat. Okay, and so to demonstrate what this looks like, if I were to, let's see, have a set of points here, and I were to draw a line through them, so in this typical plot of points of x against y's, there is a corresponding plot called our residual plot, which is plotting our predicted value of y's against the residuals. Again, so residual is equal to observed minus predicted. Let's see. So if my y's are at A, B, C, something like that, then you would have a corresponding set of points here that correspond to your residuals. It would look something like this. So here, something like this. And so the distance, oh, this would actually be, hang on, this would actually be negative. So these distances on the left-hand side are going to reflect the value of the residuals here. So in this particular example here, that would be corresponding to, say, a larger difference value here because it's farther away from my predicted y point. And so plotting the residuals against the fit, in other words, plotting your y hat versus your residuals is a really, really useful diagnostic device because it tells you something about the relation between the fit of your model against the points that are in the data. So let me draw a couple sort of residual plots, and hopefully we can get some folks to speak up or type in chat about what this would sort of infer about how our model is doing. So in a plot like this, we have our residuals versus our y-hat. Let's say we have a residual plot like this, or we have a plot like this. Okay. Can any brave volunteers chime in and tell me a little bit about what these plots might mean?
Well, the one on the right would probably suggest that your data isn't linear, so you were maybe trying to estimate it in a linear fashion, and it looks like it might have some quadratic component to it.
Okay. Great.
Yeah, I'd say the one on the left probably just means you're guessing at the wrong slope, but it's still clustered in a way that could suggest it's linear.
Yeah, great. Exactly. So let me draw some plots that may be sort of corresponding with these residual plots, and so exactly. I see a comment. So bias in our fitted values, exactly. So here, this would be our x and our y, and this may look something like, if I just sort of try and draw a similar sort of type of pattern, I think looks something like this. And notice that all the error values are above 0, so they're all positive, which means maybe my line looks something like that. And so, right, the distance from all of these guys is going to reflect sort of how the residuals turn up here. And so if I were just to look at this plot down below, it'd be pretty obvious, right? You could say, oh, obviously the line isn't going through all my points, and clearly the fit is not good. It's obviously biased downwards for some reason. And so what I would like for you to be able to do is to be able to interpret the residuals in the same way, where you can, in the same way where I can look closely at this plot and see that there's something wrong, you should also be able to look at residuals pretty quickly and see that there's something wrong. So let me draw this example as well. So here we have large negative, small negative, and then a larger positive, right, going through R here. And so if I were to draw a line here, your first set ones would be sort of largely negative, and then it might look something like this, right? And so the shape of these of the fit versus the data points is actually going to look similar to the spread of the residuals against your fit in this particular case. And so what are we looking for in our residual plots, where, you know, hopefully for a lot of you, it's sort of immediately, the two examples that I'm giving immediately strike you as being weird in some case. Really, we want our data to be sort of populated sort of around our fit line, right? And so that would have a corresponding effect in your residuals of having points sort of be randomly distributed around my my 0 point, right? And so that would indicate that besides the sort of like random noise from the error, that our model is able to describe a fit wherein things are sort of in a random cloud in my residuals around my 0 line. So one thing you might be thinking to yourself is like, okay, why do I care about looking at the residuals versus just interpreting sort of the two plots on the bottom, right? Because then I could look at that and be able to quickly tell. And so one of the reasons why residuals, besides all the like sort of statistical and mathematic sort of properties of residuals that allow you to do diagnostics, one of the things about residuals that is really handy is that it reduces everything into a strictly sort of two-dimensional comparison between my fit and my error. So while in the examples that I'm giving, it's like really easy to see in the bottom plots, what if you had 2 x values or 3 x values or 100 x variables? Yeah, not values, variables. So you have x1, but you also have x2 and x3 and so on and so forth. Suddenly, you know, even with 2 x's, now you're suddenly trying to envision like the fit of points in a cloud going through, and how that relates to a point in like 3-dimensional space. So suddenly it gets really hard to visualize, right? So that one of the sort of qualitatively handy things about the residuals is that I can sort of easily do a diagnostic about whether or not my errors are distributed randomly about my about the fit of the model that I've created, even in multi-dimensional space. So hopefully that makes sense to everyone. Okay, let me see. Yes, so I see a comment. There's a common assumption in statistics that errors are normally distributed. Yeah. So that is one of the common properties in like a linear regression. And so what would that mean for residuals? So actually, let me draw a plot of this. That's exactly right. So one of the things that we would expect is that there is a normal distribution of errors, which means that across my 0 value in my residuals, you would expect some kind of spread of values of your residuals to sort of fall within some standard deviation. Oops, you would expect you would expect your the spread of the values to fall within you know, 1 standard deviation, 2 standard deviations, something like that. And so if you had residuals that were evenly distributed around my around the 0, but that weren't normally distributed. So let me draw an example of that. So like, say you had something that looks like this. Even though, you know, the fit of our data is sort of like even around the sort of positive and negative values, we would actually think that this is a little bit weird. There's probably some bias in the model that we haven't sort of captured, because it looks like here the errors aren't sort of really distributed normally about my 0 point. So that's sort of one additional thing to keep in mind. Okay, and so sort of building off this topic of residuals, you know, what we're trying to do in this class and to and in this particular set of examples is to kind of try and build up a set of tools that sort of really make sense qualitatively to you for doing all sorts of data analysis and regression. And so here we're talking about diagnostics, right? And so the sort of common go-to examples, again, is the R-squared and standard error. And they are useful metrics, but again, don't extend the interpretation of what those values are to beyond what they actually mean. And so we are diving into a set of tools that hopefully you are able to understand the importance of through these sort of demonstrated examples. So one of these is the residual plots. I always recommend when you're doing sort of linear regression and any sort of regression modeling, take a look at your residuals, because they're going to tell you a lot about bias in the fit of your model, right? You could have an amazing R-squared and great great coefficients that are highly significant, but if you don't take a look at your residuals, you could end up with a biased model and you wouldn't know, right? And so it's a really important tool to take advantage of. So another question, should standard errors always be normally distributed, or is it only for linear regression? So standard error is always assumed to be normally distributed. That's different from what I was talking about before, which is the distribution of errors in your regression model. Okay, so those are two separate things. The standard error in the context that we've been talking about so far is referring to the error in my estimate of the mean value of my coefficient. In other words, the mean value of the slope of the line, and that is typically that standard error describing that mean is always normally distributed. Yes. So one of the things that we can do is actually actually the next point that I was going to talk about is related to the previous question before Vishnu's, thinking about the error about my line. So this is actually another sort of diagnostic device that is not as common, but sort of leads us to think about ways of doing diagnostics that are more common. So this is a residual standard error. So this is the standard deviation of residual values. Okay, and so what does that mean? Qualitatively, we can sort of think of this as what is the spread of points about the regression line. So I'm going to write the equation sort of just for your reference. It's not like it's something that you have to memorize or anything. But for those who are interested, the residual standard error is equal to 1 over n minus 2, the sum of I equals 1 to n of yi minus yi hat squared. So this is essentially telling you, if I were to look at my residual plot again, y hat and residuals, you may have something that looks like this compared to a residual plot that looks like this. Okay, and I sort of tried to draw the same points between here and here, but that the points are all sort of tighter around 0. And if you imagine that there were the same sort of data set and you're running 2 different models, and one of them gave you residuals that look like this on the left, and one of them gave you residuals sort of on the right, one of the things that we would be able to say, like, think about what this would mean qualitatively. Essentially, our model is able to get closer to our observed points than in model 2. So if I call this model 2 and model 1, in the second example, you are able to get sort of closer to your fit than in model 1. And so that's one sort of common way to think about this. And this is actually the basis for a much more common metric called the mean squared error. So, and I should note before, so a lot of times people compare residual standard errors to the mean value of y, because it compares sort of the spread in the 2 cases. A much more common metric is called the mean squared error, also known as the MSE. And it looks actually fairly similar to your residual square standard error. So mean squared error. And so this is, I think, a really valuable diagnostic device. And we're going to be using this sort of throughout the course. So it'll be definitely really important to get a good firm understanding of what the mean squared error is. So this is the average of the squared errors. So MSE is equal to 1 over n equals 1 to n of yi minus yi hat, and taking that difference squared. Okay, so what is the mean squared error sort of qualitatively? It's essentially the average size of your errors, right? And so in my residual plot, essentially the farther away my residuals are from 0, then the larger my mean squared error is. And so in the previous example where I'm giving model 1 versus model 2, it's a similar sort of metric, right? Because the tighter the residuals are around 0, then the smaller my mean squared error is, but also sort of the less, essentially the less the average error overall is in my model. One of the things about the mean squared error that is different about, say, a more traditional sort of diagnostic device such as R squared is that the mean squared error, as you can imagine, is going to vary from data set to data set. And so if your y model is equal to beta x plus this, so suppose that this is describing, okay, I'm just gonna throw out something like a market share or something, versus in a different example, maybe it's GDP, and market share is in terms of percent, and GDP is in terms of like billions of dollars. Right, your mean squared error is going to be dependent on the magnitude of your y, and so you can't compare mean squared error in a model, you know, describing something on sort of a percent scale, in which case your mean squared error might be like less than 1, for example, versus mean squared errors in a model describing GDP, in which case your mean squared error might be on the order of you know, millions or billions. And so what you can do, however, is that if you were to use an identical y and you are testing a variety of models on one specific outcome, you are able to do comparisons of your mean squared error across these different models, because you're looking at the same explanatory variable. And so this, I think, is at the end of the day a really useful metric, because it's essentially telling you how good you're predicting, right? The smaller your mean squared error, then the better, or the closer your model fit is to the points in reality. And so this is a pretty powerful tool that allows you to look at these, look at a sort of really direct comparison in the strength of predictions between models that are looking at the same outcome. Okay, so let's, I actually got a couple comments from people. 2 hours is a pretty long time, especially for listening to me online lecture. So what we're gonna do is around halftime, we'll do a quick sort of 5-minute break. And so we'll do that here, and let's reconvene in 5 minutes at 11:10, so that we can do a quick sort of bathroom and water break and brain break, most importantly. In the meantime, if anyone has questions or you're confused about anything, I can help clarify that right now. But we'll continue in at 11:10.
Hey, Alan.
Yeah.
I jumped in a little bit late today. When you were comparing, like one of the first exercises you did, you were comparing like those two models where you were using different values for the slope, I believe.
Mm-hmm. Yep.
I guess I was just confused, like why you had to even like include a guess for the slope.
Okay. Yeah. So there, the sort of punchline of what I was trying to show here is that I can come up with an example. So first of all, everything is based off of, if you're looking at this screen, a true model, which we created artificially. So we know what the true model is of a relationship between y and x, where you have x is x times 0.5. So we know that that's the real coefficient, and we can create a regression model that will estimate that, and it'll give approximately 0.5. And there's two different models here. In the second example, the deviation is twice as large. This manual calculation of the standard error and R squared is a way that I'm sort of bypassing the built-in functionality to see what would happen if I were to incorrectly put, or if I were to give the standard error in R squared of an incorrect estimate of beta, which I know to be incorrect, okay? And what I'm trying to demonstrate here is that I can actually come up with an incorrect beta in this one model that ends up having a more significant coefficient in terms of like your standard error and a better R squared than in a model that we know is correct.
Okay.
Does that make sense?
Yeah.
Yeah, and so that's kind of to point out that like the standard error and R squared aren't like the necessarily the correct metrics that will tell you
Right.
that your model is like biased or something like that.
All right, cool.
Yep.
Thanks. And then also I'll email you about this after class. I'm like still having trouble registering even with that PTA that Anne Marie sent me. I think
Okay.
it's something on the registrar's end. So like if you could do that thing again where you like give me permission to the Canvas page.
Sure. Yeah. Send me an email as a reminder,
Yeah.
and I'll do that. It's no problem.
All right. Thank you.
Hey, Alan. Hi.
Hey, what's up?
Yeah, good. Uh, I just posted a question. I think you didn't see it. I'll just repeat it once again. So while analyzing a model, so we got different diagnostic tools to analyze it, as you mentioned. And I got a feel that the best diagnostic tool out of the lot is the mean square error.
I wouldn't characterize it as best. I would never say any diagnostic tool is kind of the best. They all do different sorts of things. And it's I think the most important sort of takeaway that I want folks to learn from this class is to be really good at understanding what each of the diagnostic tools are actually doing. And so in your question, I'm looking at it in chat. Can we look at the mean squared error, and if it's really small, we can conclude that the model prediction is correct? Well, I mean, maybe, right? I mean, just because a mean squared error is small, it probably means that your model is doing a pretty good job at prediction, but it doesn't necessarily mean that the model is like not biased or anything, right? And so, I do tend to really favor mean squared error when it comes to data analysis, and a lot of what we're going to do, especially on the prediction end, is relying on the mean squared error. But it's not. But even I would say that it's not necessarily supposed to be the end all sort of metric for diagnostics. And really, I think that what we're trying to do is to understand how well our model does to essentially line up with data, right? Predicting on data. And there are a whole set of tools to do that. And so you should be looking at this holistically. We should still be looking at the standard error, thinking about what that means. We should look at the R squared. We should look at the residuals. We should look at the mean squared error. I tend to harp on the MSE because probably outside of like machine learning applications, it's not leaned on so much. So that's probably why I give it a little bit more emphasis.
Okay.
I think taking a step back, I do think it is valuable for people to consider it more, because I don't know, I think even if you are working in a more sort of econometric setting and you want to get at like causality, like, and some people may disagree with me on this. So this is me sort of speaking a little bit more personally, but what good is a model that isn't able to well, okay, let's put it this way. Let's say you get really accurate sort of in a more econometric context. Let's say you get really accurate like causal estimates, and when I mean accurate, I mean in the sense that like you've demonstrated really robustly that you're certain that the like independence criteria hold, and that you have like good instruments, and that you have determined a really robust causal relationship between your X and your Y. I might ask you, what good is that if your prediction of X to your Y is not accurate, right? Do you know what I mean? So even though you've demonstrated causality, your X's don't give you any sort of good relatable outcome to your Y with any sort of accuracy. I think that's really important to consider in the context of folks who do things more on a causal basis. So, okay, we'll get into that more down the line in this course.
Okay. Thank you.
Yeah. Okay. So let's continue on, and I'm jumping back over to our studio to continue some sort of base functionality and showing some of how to implement some of the stuff that we just talked about here. Okay, so one handy function related to our regression modeling is called the predict function. And so we have created a model, example model 1, which is simply our first regression way up here. Okay, so this is regressing Y on X. It's this model being described with the plot on the left. There's a handy little function called predict where I can simply put in my model object. So this is example.model1 is the object that was saved from running my linear model right here. And if you put that as an input into the predict function, it's going to give you this. Okay. What are all these values? These are each of the corresponding points of my Y for each corresponding X. Okay. So let's take a look. Let's take a look at that. I'm going to create a new column did I make it as a data table? I did, good. In my data table called predicted Y. So actually, I'm going to call it Y hat, which is our predicted Y. So Y hat is, I'm going to set as the predict of example model 1. Oh. Let me go ahead and save this real quick. That way this window will stop popping up. And my RStudio will freeze, great. Hang on. This is not an ideal time for this to happen. Okay, sorry about this, technical difficulties. although it doesn't appear to be. Okay, let's try that one more time real quick. Okay. And now I am frozen again for some reason. Apparently I'm not allowed to save. All right, sorry about this. We won't do that again. Okay, so I need to reload all of this. And in the meantime, I'm going to reset my directory to the proper location. Okay, no saving allowed. If I look at my model again, what we'll see are a whole series of y points that are corresponding to the predicted ones for each corresponding x. And just to make this sort of abundantly clear, I can make a quick plot of this so that we can see exactly what I'm talking about. So I'm going to set my x's. Oh, actually, I'm going to do two separate geom points. So I'm not going to put my AES there. So x equals x, y equals y, and we'll color these black. And I'm going to also plot my x's and y hats, and we're going to color these red. So we can see what this looks like here. Okay. So the x and y, the black points are simply the random data set that I've created, and then my y hats are the predicted points that lie along my regression line corresponding to each x. And so I can pick out an x point right here, and that lines up with a predicted y hat value here, and we can see that for every point there's a corresponding sort of y hat with a predicted point with every sort of point in the real data, right? So this one corresponds to this one corresponds to this one, and so on and so forth. And so this would be what y hat would be spitting back to us every time we put in one value of x. Okay. We can also do kind of a interesting look at another way to look at these y hats. not predicted y, y dot hat. And I'm going to actually add a little line here. Okay, so this is a this is a plot of not the just the sort of data points from before, but actually the fitted values against my actual values. Actually, I think it'll be better if I were to make the X's and Y's line up in the same axes. So give me one quick moment. Let's do -1 to 30 and 30. Okay, so I'm adding some additional options into my plot where I'm setting the limits on my axes to go from -1 to 30. And the reason why I'm doing this is I noticed that that my plot is going from 25-ish up to 30, so I just want to make it square. I think it'll be easier to sort of interpret. Yeah, okay, perfect. Okay, so if our y hat if our predicted y hat were equal to the actual y hat, it would lie sort of right on this line here, right? And you can see that they're not quite the same, and so there are some differences between my predicted value and my y value, and this is kind of the spread here. So if you if you're paying close attention, you'll note that this is actually a pretty close relationship with something else that we've looked at, which is that the difference in value between my y hat and y is actually the residuals, right? And so this is actually this is essentially the residual plot, but sort of rotated so that this line should represent the sort of zero line in our residual plot. Slightly different way of looking at it. I think that the residuals is easier because you can see things in reference to a horizontal line instead of a sloped line. Okay, so let's see. So don't worry about the code here, because this actually is the base R plotting. So actually, I'm just going to go ahead and copy and paste this in, but don't worry about this code, because it's not something that we've covered. It's using the base package of plotting for R. It's mainly so that we can look at this plot. So again, this is a way of visualizing the size of my residuals between my X's and Y's. I can actually look at, for every individual point, the distance from my point to my fitted line, and that represents the residual values. Okay, and actually this part I will try and do as ggplot. So in our model here, similar to the way that we can obtain a prediction, I can actually also grab my residuals. And the function to do that is called resid. And so actually, if I were just to, if I go ahead and run this, yikes. And I look at my data again. Where are we? Example model 1 for model, oops. Here we go. We are able to get our, so before I use the predict function to generate my y-hats, and I can use my resid function to generate my residuals. A different way I could generate my residuals is just to take the difference between my y and my y-hat, right, which is the definition of the residuals. And in fact, we can see that that is exactly the case here. 24.2 minus 17.7 is equal to 6.5. 13.76 minus 13.01 is about 0.75, and so on and so forth. And so I can also get from R, get the residuals via this function, or from doing the predict minus the y. So two different ways of going about it. And I can go ahead and do my sort of quintessential plot of my residuals as follows. So I'll go ahead and use forModel.1 as my data. And then for my aesthetics, I want to plot y-hat on my x, and I want to plot my residuals on my y. And let's add the points here. And then we can go ahead and add a horizontal line. So let's do slope equals 0, intercept equals 0. Okay, and we'll run this. And this is our residual plot. And so this is the type of thing that you usually would like to see. You have points that are essentially sort of randomly distributed around my 0 line here. I'm not seeing too much of a pattern. Maybe a little bit, in sparser in the middle, but that's, you always have to take into account that there is some sort of randomness happening here. And as a matter of fact, if I go ahead and rerun everything, let's see, how do I go about running everything? I'll just select everything. Because these points are randomly generated, I could create a new plot, right? And so this is a different set of 100 points. And in this case, again, the residuals look pretty good. Not too much sort of pattern or bias on one side of the line versus the other. Yeah, and so this is the sort of thing that you would like to see again. And as you get more experience with doing regression and data analysis, I think you'll get pretty good at understanding when you're seeing some abnormalities in your residual plots. Okay. So let's see. I think that I will. This sort of concludes the coding portion of the material that we covered today. I did mention before in previous lecture regarding looking a little bit more at examples of ggplot and doing some functionality. And so I thought what I would do now is to return to that example that I was giving before about the coronavirus, and rather than sort of necessarily walking step by step through the code, I would just sort of generate plots that folks are interested in, and then you can sort of look back at the code to see in more detail sort of about how they're done. But you know, I would still sort of go about explaining what I'm doing, but probably a little bit more quickly. And so let me pull up the code from last time and load in our coronavirus data set, and then folks can speak up about like plots that they would like to see, and I can show everyone how to do that in the sort of time remaining. So let's load this in. Okay, so as a quick sort of review of the data. Oh wait, sorry. Okay, I think I missed a question before we jump to that. Would you ever do a residual versus X plot? So let me think about that. And actually, while I think about that, let's take a look at what that would look like. So I can answer no from a practical reason, but let me think about what this means theoretically first. So residuals versus X. So, okay, well, the practical reason why you wouldn't do this is that this is only going to work for a single dimension X, whereas with Y hat, you're combining everything. And so as soon as I have like a bivariate or multivariate model, I can no longer do this, right? And so it would be really confusing to think about what residuals would mean relative to like a multi-dimensional space. Now, what would an X versus residuals, even in a univariate model, what does that mean in theory? You're essentially plotting your it's a little bit strange to interpret this way because your scale Okay, wait, let's see. So what about to see if any single predictor is behaving oddly? Let's see. Is that always the case though, that that for an independent for an individual variable that you would want your residuals to also be distributed randomly as a form of the residuals? I'm not sure. Actually, I would have to think about that. Let me make a note of that and then get back to you. I'm not. Yeah, I'm trying to visualize what that would mean sort of qualitatively, but I'm not. My brain is a little fried right now, so I'm not sure I'd be giving the right answer. So let me err on the side of caution and return back to you with an answer. Okay. Going back to this, just as a quick refresher, what we've got going on here in our coronavirus data set is, we have number of cases, population, we have dates, and we have both cumulative cases, new cases, and number of deaths from coronavirus in this data set. And one plot that we've already looked at looks something like this. I'll just sort of copy and paste this here. And so this was a plot looking at different counties within the state. How do the number of cases compare to my population? And I've separated out by facet by states. And I also have this mysterious variable that I didn't know what this was, but the magnitude of that corresponds to the size of the dots. Are there any plots that folks would be interested in learning how to do, how to look at, and how to make in ggplot? Okay, cases in New York versus California over time. Yeah, great. Okay, so we can do that. So we could actually look at new cases, and we can look at cumulative cases over time. And so I'm even okay. So probably one of the most important things is that even before I start typing away and coding a plot, is I want to be really specific and have a good idea in my mind about what it is exactly that I want to plot. And so let's see, if I want to look at let's say cumulative cases, why don't we go ahead and sort of draw a line? We'll do a line graph with let's say, a different color for each state, and we'll plot on our x-axis the date, and on our y-axis the cumulative cases, or new cases. Okay, Greg wants to look at new cases, so we can definitely do that. For new cases, I don't know why I'm thinking of it like this, but I think that, does it make more sense to do new cases as like a bar plot? And so, okay, I mean, well, I'm going to plot it as a bar plot, and then maybe we could do later cumulative cases as a line graph. So let's go ahead and put this together. One thing that I want to do, actually, even before I ggplot, is that if I look at my data set, I'll note that all the cases and everything are actually happening by county, and so I need to add it up to each state and each date. And so we can take advantage of our data table functionality to do that. So we'll do coronavirus by state. And so I'm going to take our full data set, and I'm going to create a new column called total cases. Well, actually, we'll do it like this. New cases dot new cases and total cases. And so this is going to be, half the time I spend is actually just figuring out good names for columns. So new cases is going to be, and actually, and I'm joking about that, but on a more serious note, it is worth spending time to like think about good like naming conventions, so that when you come back to your code in the future, you don't hate yourself for coming up with weird, like indistinguishable names that you don't have any idea what they're describing. So actually, it is good practice to be pretty descriptive with both variable names, column names, any sort of naming that you're doing. Yeah, you'll thank yourself later for doing that. So new cases is equal to the sum of new cases. And total cases is equal to, same as before, from our example from before, max cases. And this time I'm going to add them up by state and by date. And I believe we called it date. Yeah, that's right. Okay. So that is our data. I'll quickly take a glance at it just to kind of make sure it looks how I want it to. And then actually, I'm also going to throw in deaths. And so I actually think it's total deaths because the cases are organized the same way. So we'll just list it out like that. Okay, so ggplot, we're going to use CV by state as our data input. Our X, right, is going to be our date. Our Y is going to be our new cases, because we want to look at whether or not the curve is being flattened, right? We're going to group so that we're separating out the plots for each state. So we're going to group by state, and the colors, the fill colors for our bar plot are going to be different by state. And we're going to do geom bar stat equals identity. Okay, so there's a little option in geombar called stat, and that's indicating whether or not you want simply to count the number of entries as the size of your bar, or whether the entry itself is giving the size of the bar. And if the entry itself is giving the size of the bar, then you use stat equals identity. And then we want position. So in a bar plot, I can stack the position. I can stack the bars, or I can have the bars side by side. So to stack the bars, it's called position equals stack, and to have them side by side, it's called position equals dodge. And I think that's pretty much it. And let's take a look at what this looks like. Oh, okay, hang on. We have like way too many states. I forgot that we were only trying to filter for California, state in California, and New York. What happened here? Oop, I have equals equals and percent in. That is an error. Okay, so here we can see the total number of new cases per day by date. And so are we flattening the curve? Yeah, and so I guess you can kind of maybe see some of that here. It's not increasing sort of exponentially anymore. There appears to be a bit of a decrease. So this is, you know, a neat sort of visualization that helps us see that the curve is flattening somewhat. Okay, I mentioned that we could also do sort of a line plot of not new cases but cumulative cases. So I'll do that real quick to show how to do that, and it's pretty similar. So the beginning part is the same. So this is look at all the data for states called California and New York. Our x-axis is going to be the same, but our y-axis is going to be describing not new cases, but total cases. And then we're going to have different line colors by state. And so we'll have a geom line, which draws the lines. And so this is the total number of cases in California and New York over time. And actually, I guess in a similar way where we're looking at new cases, I guess technically you can kind of infer sort of quote unquote flattening of the curve via sort of a change in the inflection point in the cumulative. So the concavity of your line is sort of passes an inflection point and is starting to be less sort of exponential. So yeah, maybe that's promising news for all of us, where we've hit our peak, and hopefully we'll start to decrease in number of new cases over time. Any other suggestions for ways of looking at this data? Okay, well, I guess we are getting sort of close to end of class time. Okay, yes, let's see. I have a quick request to show the columns again. Here. You've got the county locations, the dates, the number of cases, number of deaths, population. I guess I'll hold off on making new plots. If anyone sends me you know, a request in the chat right now, I can quickly put it together in the notes so that you'll have a couple more examples to refer to. But I guess probably it'll be useful for you to at least understand some of the structure of ggplot. So, you know, I'll throw these examples up and include them in the notes, and so that folks will have a couple different things to look at.
Alan, can I ask a question about the data wrangling part?
Yeah, sure, absolutely.
Okay, so I know you've explained a few times about using the period as like as part of your code, and could you just explain again like what that does?
Yeah. So in base functionality, some folks who are less familiar with data tables and more familiar with working in data frames, you can call up column names via the combine function. So I can do, you know, call name 1, call name 2. And so this is a way of referencing back to, I guess, specific items in your data frame. So data table is organized in a similar way, but instead it actually treats them as objects, because actually there's some sort of hidden functionality inside data frames or data tables that make this type of thing probably a little bit, it makes a little bit more sense to do that. And so in this way, I can reference, I reference things via list instead of C, and I reference things as without the quotes, even though that may seem a little bit weird, because traditionally anything without quotes is like an object, and like the name itself is kind of being treated as an object. So that's a little bit of the nuance of data table. And so if you have sort of a firm grasp of this, the only thing that I'm doing with the period is something like this. Oops. So they just made a shortcut so that you didn't have to type out list all the time. So the period in data tables, inside of the data table square brackets, is a replacement for list.
Okay, that makes sense. Thank you.
Yeah. Okay, so I think that we'll conclude today on this note. And I'm gonna stick around for a couple minutes in case anyone has any questions. And actually, I'm gonna actually go ahead and write out the last request for plotting death rate in terms of deaths per cases by state. So I'll do that sort of as I wait for any sort of last minute or end of the course questions as people trickle out. So we'll end here today unless there are other questions, and I'll just go ahead and do this last request, which I will include in the notes and that you can take a look at. Oh, actually, sorry, before people trickle out, just as a quick reminder, for the homework, please make sure that you'll be turning in the documentation either, again, in R Markdown as a LaTeX document or in like an IPython or Jupyter notebook for those of you doing Python. Yeah, and that's it.
Alan?
Yes.
Can I ask you a question about doing this coursework in Python?
Yeah.
So the first homework, just that second question, is a pretty like R-specific question.
Okay, that's the one with the built-in functions, right? Or yeah, so you would have to recode that in Python, although it's like, it should be, if you're comfortable and familiar with making functions in Python, it should be really straightforward to translate them into Python.
Yeah. Well, I just have to understand what it's doing in R.
Yes, but you would have to understand what it's doing either way, right?
Yeah. But I guess my question is, how many more things like that should we expect? And in like the future homeworks, will it be more kind of agnostic to?
Yes, I see what you're saying. Yeah. So in the second homework, there is going to be something like that, but you know what? I can. Yeah, I've sort of let the Python users sort of be on their own for that type of thing, but you know, I can just go ahead and make the equivalent Python functions too, and update the homework. That's actually, it really isn't that hard to do, and so yeah, I believe that that it should be all right to, or there isn't so much more in that kind of structure. I think there's only one other problem in homework 2 that's sort of like decipher the code type of thing. But I kind of will point out that eventually we will get to, I'm sort of thinking ahead. We will get to some functionality and packages in R that are specific for types of statistical analysis, and they're fairly specific to R. And I would imagine that those types of things exist in Python, but you will be kind of on your own in figuring that out. So just kind of as a heads up. So I'm referring specifically to doing like general additive models and doing like spline operations in Python, which I'm certain will exist, but again, the coding portion is going to be you'll have to figure out how to do that in Python.
Okay, you said general additive models, and what was the other one?
And spline regressions. And there may be like a couple other examples, but that type of stuff. I would imagine that you'd be able to find them in Python, but it's kind of just a heads up for you that we'll be leveraging these packages in R that are specifically designed to do those sorts of operations.
Yeah, I'm kind of trying to decide what is the best way to approach this class. If I should just kind of try to get a good enough understanding of R and just do it through R, or if it makes more sense just to practice Python.
Yeah, hang on. Let me actually just stop recording for a sec.